This is the solution for the graph of f of x equals x e to the negative x to do a complete curve sketch for calculus 1. Right, so we're doing a complete analysis of f of x equals x e to the negative x, which is also the same as x over e to the x. We'll use that as necessary. All right, the domain is all real numbers. This is defined all the time. When you think of it like so, e to the x can never be 0. So it's always positive. So this is defined for all real numbers. Intercepts is the origin. You plug in 0, you get 0. If you said y equal to 0, then the numerator has to be 0. That also gives you 0. Okay, there is no symmetry. F of negative x is negative x e to the x. That's not the same as the original. That's not the opposite of the original. So no symmetry. Asymptotes. This is where you want to figure out limit x approaches infinity of x over e to the x. That's infinity over infinity. So by L'Hopital's rule, it's the same as the limit as x approaches infinity of 1 over e to the x, which is 0. So the graph approaches the x-axis, y equals 0, as x goes to infinity, as we'll see from the graph here eventually. And when x approaches negative infinity, y also approaches negative infinity. If I plug in a super big negative number, negative x, that's a large negative. E to the negative will be a big positive. So a big negative times a big positive will be a big negative. So the graph goes to negative infinity as x approaches negative infinity, like so. All right, so for the first derivative, we're using x e to the negative x. So first function times the derivative of the second. The derivative of e to the negative x is negative e to the negative x. Plus the second times the derivative of the first is e to the negative x. Factor out the e to the negative x, you have 1 minus x e to the negative x is the best way to think of it. Second derivative, first function 1 minus x times the derivative of the second. Derivative of e to the negative x is e to the negative x times negative 1. Plus second function e to the negative x times the derivative of the first, which is negative 1. Factor out the e to the negative x. And then if I apply the negative 1 to the 1 minus x, that gives you x minus 1 minus another 1 gives you x minus 2 e to the negative x. Set f prime of x equal to 0. 1 minus x e to the negative 1 equals 0 means x equals 1. That's 1 comma e to the negative 1 or 1 over e. You always want to write the exact value whenever possible. I put the 0.37 just to know where it is on a graph, but you should always write it as either e to the negative 1 or 1 over e. That's called the exact value. Sign chart for the derivative. If I plug in 0, I get a positive. Plug in 2, I get a negative. Remember, e to the negative x is always positive. So the function is increasing from negative infinity to 1. F is decreasing from 1 to infinity. And you have 1 comma 1 over e is a maximum. So increasing, decreasing the rest of the way. And set y double prime equal to 0. X minus 2 e to the negative x equals 0. That means x equals 2. Again, that cannot equal 0. That comes out to be 2 comma 2 e to the negative 2. 2 e to the negative 2 or 2 over e squared. Yes, it's about 0.27, but you should leave it as exact value. Sign chart, again, keeping in mind e to the negative x is always positive. If I plug in 0, I get a negative. If I plug in 3, I get a positive. So concave down, concave up. So f is concave down from negative infinity to 2. F is concave up from 2 to infinity. So my inflection point is 2 comma 2 over e squared. So here's our graph. Only intercept maximum at 1 comma 1 over e. Inflection point 2 comma 2 over e squared. Increasing, decreasing, inflection point decreasing in a concave up fashion. Asymptote is the x-axis, and there's the entire graph. Right, so that's the complete analysis of f of x equals x e to the negative x.